Welcome to today's paper reading. Today's paper is titled LLM2LLM, Boosting LLMs with Novel Iterative Data Enhancement. This paper was published on the AR14 preprint by Nicholas Lee and colleagues from UC Berkeley. The research aims to solve problem X by investigating Y. The research focuses on Z and its impact on A. Understanding problem X is essential to advancing the field of Y. Previous research has shown B, highlighting the need for further investigation of Z. The introduction of LLM2LLM presents a novel approach to enhancing the performance of large language models in low-data regimes. LLM2LLM is a targeted and iterative data augmentation strategy that employs a teacher LLM to generate synthetic data based on errors made by a student LLM during fine-tuning. This process involves three key steps. First, fine-tuning a baseline student LLM on an initial seed dataset. Second, evaluating and identifying data points that the model incorrectly predicts. And third, using a teacher LLM to create synthetic data from these incorrect points, which are then reintegrated into the training dataset. This method aims to focus on more challenging examples, thereby improving the model's performance. The results demonstrate significant enhancements, with improvements of up to 24.2% on the GSM-8K dataset, 32.6% on casehold, and 32% on SNPs, outperforming traditional fine-tuning and other data augmentation methods. In the realm of instruction following large language models, LLMs, early works focused on fine-tuning using existing NLP datasets. The self-instruct framework introduced by Wang et al., 2023, innovated by bootstrapping instruction datasets using the model's own outputs, reducing reliance on pre-existing datasets. Follow-up studies leveraged stronger models to fine-tune more capable general-purpose instruction following models. On the topic of self-improving LLMs, various early works explored self-improvement techniques, typically filtering model outputs before fine-tuning. LLM2LLM stands out by not directly fine-tuning on its own outputs, and using a teacher model for synthetic data feedback. Concurrent papers have also adopted iterative approaches to enhance LLMs, often combining ideas from reinforcement learning and self-play. LLM2LLM differentiates itself by focusing on low-data regimes for task-specific fine-tuning. Regarding data augmentation, traditional methods in NLP augmented data at the character and word levels. Recent approaches use LLMs to synthesize new training data, with notable examples like AugustGPT. Recent studies have shown that significant results can be achieved with smaller subsets of synthetic data, challenging the need for very large datasets. Figure 1 illustrates the LLM2LLM process, which enhances large language models, LLMs, through iterative data enhancement. The process starts with training and evaluating the model on the training data. Incorrect answers are then used to generate additional samples similar to the teacher model's style. A new student model is trained using both the original data and the newly generated samples. After fine-tuning, the model is evaluated again to identify incorrect answers, which are used by the teacher model to create more data points testing similar concepts. These synthetic data points are integrated back into the training dataset, and the process repeats, progressively refining the student model with more targeted data points. The methodology presented in this paper introduces an iterative data augmentation process called LLM2LLM. This process involves using a teacher model to generate new training data based on the errors made by a student model. The key steps include fine-tuning the student model on a seed dataset, evaluating its performance, filtering out the incorrect answers, and then using the teacher model to generate new, conceptually aligned data points. This method focuses on the challenging examples that the student model struggles with, rather than indiscriminately expanding the dataset. The results show significant improvements in test accuracy, especially in low data regimes, outperforming baseline methods that only use the original seed data. This approach not only enhances the dataset quality but also demonstrates the effectiveness of targeted data augmentation in improving model performance. Table 1 presents the performance of LLM2LLM across various datasets, highlighting significant improvements in test accuracy, particularly in low data regimes. For instance, on the GSM-8K dataset, LLM2LLM achieved a 24.2% increase in accuracy compared to baseline fine-tuning. Similarly, on case hold, the improvement was 32.6%, and on SNPs, it was 32%. These results underscore the effectiveness of LLM2LLM in enhancing model performance with limited initial data. Figure 2 illustrates the performance of the LLM2LLM framework on GSM-8K and case-hold datasets with varying seed data sizes. Each line in the graph represents the test accuracy of the fine-tuned Llama 2-7B model after each step of LLM2LLM. The x-axis shows the total data size, which includes both the seed data and the data generated by LLM2LLM. The graph demonstrates that by iteratively applying LLM2LLM with low amounts of seed data, significant performance improvements can be achieved, sometimes even surpassing the performance of simply annotating more real data. In this section, we evaluated the performance of LLM2LLM by fine-tuning Llama 2-7B on various datasets including GSM-8K, Casehold, SNPs, TREC, and SST2. We used different sampling rates from 0.02% to 50% to assess performance across various low data regimes. The teacher model for these results was primarily GPT 3.5. We observed significant improvements in accuracy, for instance, boosting test accuracy from 0.99% to 19.56% on GSM-8K with only 1% of the training data. This performance enhancement was achieved through iterative data generation based on model mistakes. Additionally, LLM2LLM outperformed other augmentation methods like EDA and AugustGPT, especially in generating more targeted examples where the model struggles. The choice of teacher model also played a crucial role, with stronger models like GPT-4 Turbo yielding higher quality augmentations and better accuracy. Table 2 presents the results of LLM2LLM compared to other baseline methods. It shows that LLM2LLM significantly outperforms traditional fine-tuning, EDA, and AugustGPT methods by generating more targeted and effective data augmentation. The table also highlights that the choice of teacher model impacts the quality of augmentation, with stronger models like GPT-4 Turbo producing higher accuracy. This demonstrates LLM2LLM's capability to enhance model performance through strategic data augmentation. Table 3 compares the performance of LLM2LLM's iterative augmentation approach against the one-shot augmentation method using 100 seed data points. The table shows that for the GSM-8K dataset, a one-shot augmentation achieves 16.3% accuracy, while the iterative approach, with 10 steps, achieves 23.73%. Similarly, for the casehold dataset, the one-shot method reaches 59.94% accuracy, and the iterative method reaches 64.5%. These results demonstrate that the iterative approach significantly outperforms the one-shot method, justifying the design choice of generating one data point per ROM example in LLM2LLM. Table 4 presents an ablation study on the effectiveness of augmenting previously generated LLM2LLM data. The study compares augmenting only the seed data versus also re-augmenting the augmented data. The only August seed data column indicates whether only the seed data is augmented. The total August column represents the total number of augmentations generated over 10 steps of LLM2LLM. The ACC column indicates the final test accuracy. The results show that augmenting only the seed data leads to better performance, highlighting the importance of maintaining the original data distribution during augmentation. Table 5 presents an ablation study comparing the effects of fine-tuning from scratch versus continuous fine-tuning. The study highlights the total number of augmented examples generated over 10 steps of the LLM2LLM process. Key findings include the accuracy differences observed on the GSM-8K and casehold datasets when using these different fine-tuning strategies. The LLM2LLM framework is an adaptive and iterative data augmentation method that significantly reduces the need for real data by scaling with synthetic data. This approach has shown substantial performance improvements, such as a 24.2% increase on the GSM-8K dataset, 32.6% on casehold, and 52.6% on TREC. However, The method is primarily effective in low data regimes. Future work could involve tuning the framework's hyperparameters and integrating it with other LLM techniques like prompt tuning and few-shot learning. Thank you for watching.